See,
And now try
that's a stronger one.
That's a stronger one?
And this is the weaker one.
Okay, what happens when you try really, really hard? Like, does it hurt or you just can't do it?
You just can't do it.
Ed Trapno, my grandfather, has lost muscle mass and range of motion in his shoulders, making simple daily tasks frustrating or even impossible. Sarcopenia is a medical condition characterized by the decline in muscle mass and function with age and is experienced by 75% of men over the age of 85. This is not only a problem for millions of other seniors like Ed, but also their families, physiotherapists, retirement homes, long-term care facilities, and hospitals. Our team understood this problem and noticed there's no assistive device commercially available that can reduce the strain of this condition, while also being affordable, comfortable, and easy to use. Now introducing our product, Exo, by Sarah, Jake, Kate, Shannon, and Beatrice. Exo is a localized exoskeleton that increases the range of motion and power of the arm, and subsequently the independence of the individuals affected by degenerative muscle conditions. Our device uses sensors to autonomously gently raise and lower the upper arm when it detects the user's attempted movements. The Exo is designed to be lightweight and discreetly worn underneath clothing as to not disrupt daily life and naturally help affected individuals.
Before brainstorming ideas for our device, we came up with a list of requirements and objectives that our solution must meet. These requirements included lifting the right arm forward at least 75 degrees, moving the arm at an average speed of 45 degrees per second, raising the arm with an additional 1.5-pound object, which we estimated to be the average weight of a full cup, detecting an attempt at moving and responding within 3 seconds, operating wirelessly for at least 30 minutes, being able to be put on with assistance in under 1 minute, costing less than $500 to be affordable and accessible to the general public, and weighing less than 15 pounds to minimize extra stress on the body.
To generate design concepts, we completed C-sketches and researched sensor options. Our C-sketch concepts were evaluated based on their cost, weight, speed, discreteness, and ease of construction using a weighted Pugh chart. Sensor options were evaluated based on their cost, response time, and ease of implementation using the same method. Our most promising design was a design with pulley actuation and a piezoelectric flex sensor for control. This option scored well in all of our evaluation categories. We then evaluated and refined our design with iterative testing using physical prototypes. Prototypes included a wooden mock shoulder, where we used a universal joint to simulate the shoulder's range of movement. This prototype was used to easily experiment with different pulley arrangements, motors, and string routing for our final design. We also assessed a second design option, which consisted of an inflatable sleeve to raise the arm. This was evaluated using a bike inner tube.
Mechanically, our project went through a lot of iteration, testing, and discussion. Our product works mechanically using a cable system connected to a motor and spool assembly. Put simply, the cables are reeled in around the spool, through the cable guides along the user's bicep, and down to their elbow, where the cables are anchored. There is also a pulley on the shoulder to provide extra comfort, reducing the friction in this high-stress area. The motor drives the belt which winds the pulley, bringing the user's arm up in front of them, 90 degrees in relation to their chest. All of the above systems are mounted to a custom back and shoulder brace, which attaches around the waist, chest, shoulders, and bicep of the user. We knew that to prevent the motor from moving up the user's back, we would need to have a rigid surface to mount it to. To do this, we embedded a welded steel cross-section inside the back brace. This not only provides a solid mounting surface for all of our components, but helps keep the user's posture in the upright position. For the cables, we decided on using fishing line because of its high tensile strength of around 50 pounds, as well as its low coefficient of friction. This allows for smooth movement through the cable guides without bunching or tangling.
We selected a stepper motor to provide the lifting force for our device. A stepper motor was chosen because it has the advantages of being able to accurately control the motor position, it can hold a stationary position, and can rotate continuously. The required motor torque was calculated using a free body diagram with the weight and weight distribution of an average 65-year-old male's arm. This was then verified with physical testing. The motor selected is a NEMBA 17 bipolar stepper motor. This motor was selected because it has a high torque to meet our torque requirements, low current draw to meet our device's battery life requirement, and has a small form factor suitable for a discrete device.
The mechanical advantage system was one of the key components of our project. Through research, we knew that a stepper motor of reasonable size and weight would not have enough power on its own to meet our requirements. We considered several systems to compensate for this lack of power, like a pulley arrangement or a gearbox. We decided on a belt drive and a 20 to 60 tooth arrangement. This gave us a 3 times increase in power from our motor to the reeling spool and allowed us to lift the arm. The belt drive is quiet, simple, and cheap to implement. The only issue we had was tensioning the belt, as it would skip teeth on the cogs under load. To fix this, we added a free spinning cog as a belt tensioner, which resolved the issue.
The tension force applied by the motor in our final device was 8 pounds, which is 24 pounds with the belt drive.
An initial small lift at my shoulder created a moment arm large enough to overcome the weight of my arm. As you can see, my arm lifts to 90 degrees and I'm applying zero force to keep it from falling down.
The flex and stretch sensor function was evaluated by testing their ability to sense shoulder movement when attached to different parts of the shoulder and upper body.
The flex sensor works by detecting changes in resistance when it is bent or when a force is applied to its surface. With the sensor positioned on the front of the shoulder, it can accurately detect movement in the arm. When the arm is by the user's side, the sensor is bent over the shoulder, relaying a higher resistance value. As the user lifts their arm, the sensor begins to straighten and the resistance values decrease. The only issue with this sensor is that beyond 50 degrees, the sensor cannot be straightened any further and therefore does not detect any changes. Our other option is the current sensor, which detects changes in current. When the user's arm is by their side, there is maximal resistance against the turn of the stepper motor. As the user tries to lift the arm, the resistance will decrease, decreasing the current draw from the motor. The current sensor can be easily integrated with our device and will accurately detect changes from 0 to 75 degrees, which is our targeted range.
COVID-19 prevented us from properly integrating and testing our code with the current sensor, but the logic is as follows. Again, with this sensor, the user keeps full control by still needing to use their own strength to either keep their arm moving upwards, or to hold it, or to slowly release it downwards. All these actions are read by the resistance the user applies on the stepper motor when he moves his arm. As resistance to the stepper motor turning increases, its current draw increases. First, it reads what a normal benchmark current is when the arm is resting by the user's side. Then, upwards movement is associated with decreasing current and continues to be applied until the user stops using their own muscles to lift their arm with the device. When the user rests, the stepper motor will lock and hold its place until either the user applies a downward force or as a failsafe until 10 seconds pass. That downward force would trigger a slow downward release until the current is relatively equal to what it was read at originally. When restarted, the system will readjust its benchmark current value.
Our device uses the Arduino Uno microcontroller because it is an inexpensive and well-documented microcontroller. We selected the A4988 as a stepper motor driver. This driver directly controls the current of the motor, and it's more efficient than other motor controllers like the L298N, which allows us to use a lower voltage battery. Included in the circuit is a 10 microfarad decoupling capacitor to protect the driver from voltage spikes. From research, we determined that the highest voltage we could obtain from a battery with a suitable weight, size, cost, and capacity is 22.2 volts. With iterative testing, we optimized the speed and torque of our device running at this voltage. Two 11.1 volt lithium polymer batteries in series will provide the required voltage and capacity to operate the motor at a suitable speed of a 700 microsecond pulse interval. These batteries are also rechargeable. The Arduino is powered by a separate 9-volt battery. A 9-volt battery is an economical, light, and easy to replace battery suitable for powering the Arduino and the motor controller's logic. The electronic schematic of our device is shown here. It has an Arduino Uno microcontroller, an 84988 stepper motor driver, and a Hall effect current sensor to sense the user's arm movement and control the device. Shown in this photo is our device's final electronics.
Putting on the exoskeleton is fairly straightforward. It can be done with no external help if the user is fairly mobile, like me in this case. However, for someone with less mobility, it is possible to put it on with someone's assistance. The user begins by inserting the right arm all the way through the blue sleeve, and next the left arm through the shoulder strap. Minor adjustments can then be made by tugging on the blue sleeve so that the guides are aligned in a roughly straight line. Next, the brace is adjusted with the waist strap. Note that the back of the brace tends to shift upwards when putting it on, so it is important to nudge it back down during the waist adjustment step. It should be as tight as possible while still being comfortable. Once that step is done, it's time to adjust the shoulder strap. It is passed into a loop to then secure it with Velcro on the upper chest. Further minor adjustments may be needed at this time to make sure the garment is tightly fitted at the shoulder. And lastly, the elbow strap is secured tightly. If the user is putting the garment on alone, doing it in front of a mirror is recommended.
After constructing a working prototype, we found that it took 1 minute to put on without assistance and was comfortable to wear. Using basic lifting code, the device lifts the user's arm 90 degrees from resting in the span of 6 seconds, which is slightly slower than the 45 degree per second speed we were aiming for. After weighing all of the brace components together, the total weight comes to 2.5 pounds, which is well within our 15-pound requirement. We also came in well under budget, meaning the brace will be much more affordable than other options currently available. To develop an even more functional prototype, the next step is to add an independent power supply into the brace's electrical system. This way, the brace will be powered wirelessly, and the user will be free to move around wherever they need to. Secondly, we will integrate and test the code that's been written, and adjust it until the brace can sense and react to attempted motion from the user. We will then continue to test and refine the brace to ensure that it is able to lift the arm at a more comfortable rate both on its own and when the user is holding a 1.5-pound object. In conclusion, we have created a comfortable, lightweight, and easy-to-use prototype of an arm brace. This will help people with sarcopenia to lift their arms and give them an extension on the range of motion that they were capable of on their own. Thank you for watching.